Hello everybody, we're on to our 11th video in the series of Biz Stats, and we're thinking about hypothesis testing. Just in case you're wondering what's the change of scenery, I'm recording this next couple of videos while I'm away camping with the family, and beautiful Australian bush in the background. Probably a few weird sounds you'll hear in the background too, with a bit of activity that's happening around about. But we'll get on to much more exciting things, which is hypothesis testing. By the way, you'll see that whilst we're camping, it's very cold, so I've got the puffy jacket on just to keep myself warm. So what's hypothesis testing all about? Well, the idea is what we're doing here is something that's very popular and very widely used in pretty much any of the areas of science, and that is the way in which we acquire knowledge, or at least Western science. We acquire knowledge by essentially forming hypotheses about the way the world works, and a hypothesis is sort of like an assumption or a belief or a view or an opinion, and it may be based on experience or something else. And then we need to test whether that hypothesis is likely to be valid or not. And the way we test it is with some data, and then performing some kind of analysis, or in this case statistical analysis, with that data to see whether the data supports the hypothesis or provides evidence against it. And that's essentially what hypothesis testing is all about. It's a little bit more to it than that in terms of exactly what hypotheses you test and how you go about this process, but essentially that's the intuitive idea about what you're trying to do whenever you do hypothesis testing. So let's look at a very specific example so we can get our head around this. You may recall we've been looking at a data set before now which is about incomes of people in the USA, but this is a sample of people from a particular state, New York State, in a particular age group, 20 to 30 years old. Now, suppose we knew that we've got the data from the tax office of every single individual in the country, and we know that that average income across all these people is $34,100. We might be interested in a question, a hypothesis, or in this case, a question we're wanting to look at, and that is whether or not this segment of the population is typical of the rest of the country, or perhaps do they earn less than the average or earn more because they're based in New York or because they're young. So we'd like to sort of use some data to explore that question. And we don't have any strong views about whether or not they're likely to be earning more or less. So how do we go about that? Well, first, these are the steps that we'll follow. First of all, what we have to do is, hypothesis testing is done in a reasonably formal way, and that is we specify what we call a null hypothesis, H0, and an alternative hypothesis, H1. And the null is the sort of conservative belief that we have about the world. So in this case, we don't know if these people are different to the typical American, so let's assume that the null hypothesis would be that they are typical Americans. There's nothing different about them compared to the average American income. So the null is that the income of people in New York State in this age group have an income of $34,100. So when we specify the null, that's usually our conservative position. It might be that the effect of this advertising campaign on sales is going to be very small or non-existent. So our null hypothesis is this campaign will not affect sales. And then what we're doing is looking at an alternative hypothesis, which is sort of the opposite view, which in the case of an advertising campaign is that the campaign will work. It will actually improve sales. Okay, so that's quite important, that first step of formulating the null and alternative, and there's a bit of a convention about how we do it, starting with a conservative view and looking for evidence in the data against that view. Another way in which we do that, for example, is if we were working in the legal area, and the way a system works is that people are assumed to be innocent unless they're proven guilty. So the null hypothesis in that case is this person who's being charged with this crime is not guilty, and we're looking for evidence in the alternative hypothesis that they are actually guilty. Okay, so that's the null and alternative, very important step. Once we've done that, we have to decide something called a significance level, do some statistical analysis with a statistic and a critical value, and make a decision. Those are the 4 steps. Now, once we get to the statistical analysis, the first step, as I say, was formulating the question, and formulating that question in the form of a null and alternative hypothesis. The statistical analysis is where we get into a bit more detail about how we answer that question as to whether there is enough information in this data to reject the null hypothesis. Now, the building block of this is something called, in the case of testing the mean, something called a t-statistic based on the t-distribution. So we take a sample mean. So we've got, in this case, a bunch of people who live in New York, and we know what the mean is for those people, and we really want to essentially compare it with the 34,100, but we've only got a sample mean, so we just have to kind of bear that in mind when we do the comparison. So we have a null hypothesis that the incomes are 34,100, that's this value, and we calculate our sample mean, x bar, and we compare it with that null hypothesis by subtracting one from the other. And then we scale by the standard deviation of x bar, or the standard error of x bar, so that we get a sort of standardized measure of how far my sample mean is from the null value. And that standardized measure, under the null hypothesis, will follow a t-distribution with n-1 degrees of freedom. Now, the key intuition behind this is that if I get a sample value quite close to 34,100, then that's suggests to us that these people are quite typical Americans, that they're earning about the same as average Americans, so we would not reject the null hypothesis. If I get an x bar which is a lot bigger than 34,100 or a lot less than 34,100, then that would suggest that there's evidence against the null hypothesis. So that suggests to us that maybe these people are different, either below or above the null value. So the key quantity here is how big is the difference between x bar and mu naught. By standardizing it, we translate that question to become how big is x bar minus mu x bar on our standard deviation of x, or standard error of x bar. Is it big or small? Is it close to zero, or is it far from zero? If it's close to zero, we would say there's no evidence against the null. If it's far from zero, we would say there is some evidence against the null hypothesis. Okay, so in this case, we get our null hypothesis and our alternative hypothesis. The null is that the mean for New York people in the age group 20 to 30 is equal to the national average. The alternative is that it's not equal to the national average. We choose something called a significance level, and we'll come and think a bit about that later on. The typical thing to do is to choose a significance level of 5%. Then we calculate our test statistic by subtracting our sample mean of 33,161 minus the null hypothesis value, and then we divide by this thing called standard error, which is calculated as Sx on the square root of n. So Sx was 36,001, n was 4,692, so we end up with a standard error of 526. Put all that together and you get a t-statistic of minus 1.78. And now all you need to do is to have some criterion for deciding, is that close to zero or is that far from zero? You can't just look at the number and say it's close or not close. You have to have some criteria, some means of judging. And that's actually where the significance level comes into play. What we do is we look at the t-distribution and we use the t-in function in Excel, in two direction, that's why it's 2t here, to work out the critical value of t, which is the kind of cutoff point between close to zero and far from zero. And close to zero is actually related to the alpha value. So if I choose 5%, I'm going to get a critical value of 1.96 in this case. If I choose a different value, not 5%, I'm going to get a different critical value. So we'll think a bit more about that, what 5% means later. All right, so somehow, by use of the t-distribution, I've now got a cutoff point between close and not close, and that's 1.96. Now I'm looking at values that could be either bigger than 0 or less than 0, because my x bar minus mu, in this case I've got an x bar less than the mean, but I could have got an x bar bigger than the mean, in which case this would have been a positive value. All I care is it far from 0 or not, either in the positive direction or the negative direction. So 1.96 or minus 1.96 becomes my criterion. If my value of t is closer to 0 than this, then I don't reject the null. There's not enough evidence. Okay, sure, this is not 34,100, but it's fairly close, so you'd say there's not really any evidence against the null. If it was bigger than 1.96 in the positive or negative direction, I would say there is evidence against the null. Okay, and that's basically what I'm doing here. So in this case, I conclude that there's not sufficient evidence to reject the null because that t-statistic of minus 1.78 wasn't far enough away from 0. Okay, so that's the logic of performing a hypothesis test. You'll see in the next video how we calculate this number. You've seen the details here, but it's actually given to you directly from Excel, so it makes life a little bit easier getting through these steps here. You don't need to actually do these calculations. Now, there's a couple of little variations we need to think about to this problem. In this particular problem, we were interested in, and this all comes down to what are you interested in? We're interested in the question, are these New York people of this age group typical of the national average, or are they different to the national average? And we didn't have a strong view whether they're richer or poorer. We just said, are they different or not? Now, in many cases, you're not really interested in that kind of question. You're more interested in the question, are these things the same, or is one bigger than the other, or bigger than? So are New York people earning more than the national average? Or, because they're young, are they earning less than the national average? And that's fine. You just have to formulate your null and alternative hypothesis slightly differently in that case. So instead of the alternative being not equal to, in this case, if we believe it's possible that New Yorkers earn more, then we put it like this. If we think the more interesting thing is, are they earning less than the national average, we'd put it like that. So that kind of reflects a little bit about what your belief is about, what might be true, a hypothesis or a belief or a question that you're trying to explore, and often that question is a one-sided question. When you do a one-sided test, you need to look up the critical value, putting all of that alpha probability just in one of the two tails of the distribution, not in both. And that will give you a slightly different cutoff point between rejecting and not rejecting the null hypothesis. In this case, we ended up let's see, here we are, yep. So in this case, we ended up, so now we're going to write down the null and alternative differently. We believe that New Yorkers might actually earn less than, and New Yorkers, because they're from New York and because they're young, might earn less than the national average. So the null conservative view is that they don't earn less. The alternative is that they do earn less. Choose 5%, same statistic, but the critical value now is not based on TINV2 like it was a couple of slides ago. It's now based on TINV at 5% probability with this degree of freedom, and that gives us a value of minus 1.64. So the cutoff point now between close to zero and not close to zero is a little bit closer to zero, 1.64, because all of the probability is here. It's actually over this side, but it's symmetric, so it doesn't matter which side I draw my picture. All the 5% probability is all in the one tail, so that critical value is a little bit closer to zero than this critical value here, where the 5% probability is spread across two tails. So I get minus 1.64 as my critical value. The calculated value is 1.78. So in fact, this time the calculated value is further from zero. So I do reject H0, and there is an evidence to reject the null. And we conclude that in fact people from New York aged 20 to 30 earn below the national average. Okay, so the opposite conclusion in this case, because I did a one-sided test instead of a two-sided test. Now, a couple of other sorts of details to tidy up with hypothesis testing. First thing to remember, whenever you're testing hypotheses, and this is kind of almost true of any time you're pursuing knowledge, there is a chance you'll get it wrong. You're trying to answer questions that you don't have the definitive answer to. You're just looking at evidence and see whether that evidence actually can provide you with a conclusion one way or another. There's a possibility you made a mistake in your conclusion. And so when we formulate hypotheses this way, we can document the two types of mistakes you could make, and we can have a little bit of a say about those types of errors. The first type of error would be to come to the conclusion that in fact the null hypothesis is false, when in fact it is true. That's possible to do, okay? Because we only got a sample of, in this case, for example, we came to the conclusion that New Yorkers earn less than the national average once we did the one-sided test. Well, that could be a wrong conclusion. We only had a sample of 4,000 people from New York. There's a lot more than that living in that country. It's just a sample. It's possible that this value doesn't represent, this 33,161, doesn't represent the average New Yorker, and that the average New Yorker is closer to 34,100, perhaps even more. And so we may have made a mistake when we came to the conclusion that they earn less. That may have been wrong. If we make that mistake, we're rejecting the null hypothesis when it's true, and we've made what's called a type 1 error. Now, type 2 error is the opposite. In the first time we did this test, when we did a two-sided test, we came to the conclusion that because 1.78 was not further from 0 than 1.96, that we do not reject the null. So we concluded that New Yorkers aged between 20 and 30 don't earn any, there's no evidence to suggest that they earn significantly different from the national average. Now, we may be wrong. It could be that they do earn different amount, so we didn't reject the null. It could be that indeed we should have rejected the null, but we just didn't have enough evidence to persuade us that it was false. So that's called a type 2 error. Now, that type of error is also going to sometimes occur. One way to think about these errors is to think about in a law court. When someone's tried for a crime in the court, they're assumed to be innocent until you can prove them guilty. So H0 might be, the null hypothesis might be, this person is not guilty. You come along, you get all the evidence, which is like the data, and you decide at the end of collecting all the data that perhaps you're going to find them guilty. There's enough evidence to find them guilty. So you send them to jail. So you've rejected H0, found them guilty. Now, occasionally, a person is sent to jail and found guilty when in fact they weren't guilty. That's a type 1 error. The other type of error is someone who's charged for the crime, goes through the court process, and actually there wasn't enough evidence to find them guilty, so they walk away in a free person. They're found not guilty. Now, some of those people that are found not guilty actually were guilty. It's just that we didn't have enough evidence to prove them guilty. That's a type 2 error. Now, the connection of type 1 and type 2 errors to what we've been doing is this magic thing called alpha, which, remember, I talked about as almost always just choosing 5%, and in the two examples we chose 5%. What we do is we choose alpha as our way of deciding whether this particular value of my sample t statistic is far enough from 0 or not. In other words, determining my critical value. And so the traditional way of doing hypothesis testing says choose alpha to control the probability of making a type 1 error, to control the chances of sending an innocent person to jail, if you like. You want to make that small. Now, the typical way we set that is by choosing alpha to be equal to 5%, because occasionally you are going to make the wrong decision. You just don't want to find that this is true, or you don't want to reject the null hypothesis too often, so you want to limit that probability to be about 5%. Now, of course, that doesn't always have to be 5%. And if you imagine if you're perhaps sending someone to jail for the rest of their life for some dastardly crime, you might like a tougher standard than just a 5% alpha. You might like to say, look, it'd be pretty bad to send this person to jail, or if in fact they were not guilty. So we require quite a high standard of proof. What we're trying to do when we say that is, so we want a low probability of a type 1 error. So we might choose a smaller value for alpha. But if the consequences of rejecting the null hypothesis and concluding that it's not true is not, when in fact that was a mistake, is not particularly bad, okay, suppose you say, okay, null hypothesis, this advertising campaign won't work. Alternative hypothesis, it will work. You do a little test, you get a little bit of evidence that it might work, and so you think, well, let's spend a bit more money on it. Now, if you're only going to spend another $1 million on it and you're a big company, you might think, because as long as it's got some evidence of working, we're happy. So you might choose a relatively big type 1 error, like 5 or 10%, because you don't mind too much investing more money in the advertising campaign, because you did think it worked, but in fact it's not effective. And the only way you're going to find out for sure is by spending a bit more money and increasing that impact and seeing whether it has any effect on your sales. Okay, so depending on the context, a type 1 error probability may like to be a bit smaller or a bit bigger. As a general rule, just choosing 5% is a pretty good place to start. Now, of course, as you change the type 1 error, you're going to have some impact on type 2 error. If you make it harder to find a person guilty of a crime, then there's also a better chance, an increased probability that you'll find a guilty person innocent, because you've made the burden of proof that much higher. So remembering these two things here, if I make it very hard to reject the null hypothesis, because I don't want to make a type 1 error, I'm making it easier to not reject the null hypothesis. So if I keep my type 1 error small, I will effectively result in a bigger type 2 error. So a bigger chance of not finding evidence for that. So this is quite an important sort of what's referred to as a trade-off between those two. Reducing the probability of a type 1 error will increase the probability of a type 2 error. So that's what this little paragraph here is just thinking our way through. And so we need to be mindful of that when we choose our significance level in the test, but also mindful that whenever we make a conclusion, that we may have made a mistake, and it could be a type 1 or a type 2 error. I think I'll let the Kookaburra have the last word.